Hi y'all, so the bit of class yesterday after we came out from breakout groups didn't record. So this is a quick video going over the first bit of stuff that we talked about then, the number of edges and the degrees of vertices and some common families of graphs. So let's start with complete graphs. Right, complete graphs on n vertices we usually write as kn. And what do these look like? So if n is 3, right, we get a triangle. Let's back up. If n is 2, we get 2 vertices with 1 edge. Right, n is 4, we get the outside cycle and then both diagonals, like this. Right, and then if we go up to n equal to 6, we're going to get a lot more diagonals. Like that. Okay, so we wanted to count edges, but this is a problem where it's useful to start by counting degrees. So the idea here is every vertex has an edge to every other vertex. Right, and we have n vertices total. So each vertex is going to have the same degree, right? Because they're edges to every other vertex, right? And that means there are edges to every vertex except itself. If I start here, right, I'm going to go to that one, that one, that one, that one, and that one, right? So that gives us degree n minus 1, right? An edge to every vertex except the vertex where we're starting. So now let's use degree to think about the number of edges, right? Degree in some sense counts edges. So we have degree n minus 1 for every vertex, and there are n vertices. But we need to divide because we're over counting. We divide by 2 because every edge has 2 vertices, right? So every edge is getting counted in the degree of both of those vertices. So to annotate this a little bit, right, this n is our number of vertices. This n minus 1 is the degree of each vertex. And this 2 sort of fixes our overcounting. Now let's check that this works with the examples we have here. Right, so if n is 2, we had 1 edge. That's going to work out. When n was 3, we had 3 edges. Right, 3 times 2 over 2. For 4, we get 6 edges. Right, 4 times 3 over 2 is 6. And if we counted pretty carefully, here with n equals 6, we get 15. And 6 times 5 over 2 is 30 over 2 is 15. So that matches. Now you might recognize this formula or these numbers, right? We can also write this, if you remember combinations, as n choose 2, right? This is basically how many ways can we choose 2 distinct vertices, right? And that's exactly what an edge in a complete graph is, right? We have an edge for every way we can choose 2 vertices. So that's why, if you know these 2 are equal, that's another way to find where this comes from. Okay, so let's move on from complete graphs. And talk about, we'll start with paths. So paths, if they have n vertices, we write those as Pn. Right, so here's P2, and here's P3, and P4. Okay, so let's go through and look for a pattern, right? That's a good way to do this. So here we have n equals 2, and let's use e for the number of edges. E is 1. Here n is 3, and e is 2. Here n is 4, and e is 3. So at this point, you should be suspicious, right? Edges. It sure looks like there are n minus 1 of them. So let's convince ourselves of that. We can, right, this path is sort of like extending along. So we can think of each edge as going with one vertex as sort of a starting point, right? So this edge goes with that vertex. On sort of a longer path, right, this edge maybe starts here, and this edge starts there, and this edge starts there. Right, and we're always left with an end vertex that doesn't have an edge sort of starting there. Right, but every other vertex does. And so that is sort of an informal justification for why we get n minus 1 edges. So now let's look at degree. I'm going to draw a longer path for this one. Let's look at a P6. We have two sort of distinct things going on, right? We have internal vertices, and then we have the vertices on the ends, right? And for all the internal ones, if you think about walking along the path, we have an edge coming in and then an edge going out. And so these all have degree 2. But then the end ones only have degree 1, right? So in general, we have 2 vertices of degree 1 and n minus 2 vertices, all the others, of degree 2. Okay, once we know something about paths, it's pretty easy to move to cycles. Because what's a cycle? It's a path with one additional edge. We'll write that as Cn if we have n vertices. So here's a cycle on 3 vertices. Here's a cycle on 4 vertices. Here is a cycle on 6 vertices. Right, so all we've done, for example, in this cycle on 3 vertices, is take a path on 3 vertices and then add a new edge, right? So if we had n minus 1 edges for Pn, then now for Cn, we get n edges because we just add 1. And where do we add that edge? We add it between the 2 vertices that were of degree 1 before. So now every vertex has degree 2.